Hi, I'm Andrew Duberstein, and I'd like to talk about PyDeck. PyDeck is a library for data scientists that renders interactive, large-scale geospatial data in your browser. It is similar to other mapping libraries like Folium or IPyLeaflet in that it's interactive in the browser, but different in that it is able to leverage your machine's GPU for larger visualizations. It is also different in that it's the official Python bindings to a specialized mapping library written in Uber called deck.gl. Through deck.gl, you can plot hundreds of thousands or even millions of data points, all without a specialized server. Throughout my career, I've done geospatial visualization for logistics, real estate planning, robotics, and regulatory use cases, among others. I'm currently working on fraud detection at Instacart. I'm also a technical advisor at Unfolded, which has written incredible state-of-the-art tooling for geospatial visualization. You can check it out at unfolded.ai. Previously, I was a tech lead manager at Uber, a data scientist at Uber, and before that, a data scientist for Kroger and Tesco. At these companies, I've used Folium, Leaflet.js, CartoPy, ggmaps, ggplot, QGIS, ArcGIS, PostGIS, GeoPandas, D3, and probably other libraries for map visualizations and GIS analysis. If it renders data in space, and even if it's just barely not malware, I've probably had to use it for a job or with a client at some point. PyDeck emerged from my joys and frustrations with all of these libraries. I'll talk about one use case in particular for fraud detection that made me think PyDeck would be useful. Before we start there, I would recommend that you follow along. You can see the notebooks associated with this talk at the link in the slide here. The main notebook for this talk is titled JupyterCon. I'd also recommend that you take a little bit of time to install PyDeck and make sure it's set up correctly on your machine. I'd like to start with a real use case I encountered from detecting click farms in China. Click farm is essentially a location with multiple apps and usually multiple users that are, let's say, artificially inflating click counts for advertisers, or perhaps those users are, in this case, setting up artificial accounts. They are not tied to the identities they claim to be tied to. These accounts can be sold on the dark web. They're usually trying to take advantage of things like first-time user promos. You know, that idea of sign up and get your order free, that you might first order free. You might see this on DoorDash. You might see this on Uber. If you log the location data from those mobile apps, though, you can start to combat this kind of fraud. So if you log the GPS signal from a mobile app, you can get a sense that all these phones are in the same room together, and it should look like an unexpected amount of phones in the same location. So let's take a look at that. Here's one PyDeck visualization of user sign-up locations. You can see that mostly signups map to where you would expect population density. Here's the urban core. You can expect as we get further from the city, there are fewer people and therefore fewer signups. Interestingly, there's actually one location on this map that has an anomalous number of signups. It's a little difficult to see. Here we have the same data set as above, this time rendered in 3D, also grouped to an H3 geohash, essentially a hexagon shape. So if we scroll over, mouse over the honeycomb, we can see the number of signups that happen in a particular area. If we hold Command or on some machine Shift, we can move the map throughout 3 dimensions. And of course, we can instantly identify that location with an anomalous number of signups here in Ningbo. You'll see that there's a lot of power here in that we're not downsampling the data set to be able to do this. We're not censoring the data in any way to be able to do this. And you can start to pick up on trends in these uncensored, undownsampled data sets that you could not pick up if you were using another library that might have to downsample data in order to render it. That's one quick demo. I want to talk a little bit about how PyDeck actually works. Then we're going to review some visualization examples and go through line by line. PyDeck is actually just a wrapper around another library called deck.gl. It's a JavaScript library. It's particularly performant because it relies on the JavaScript API called WebGL, which renders high-performance interactive graphics in 2D and 3D. WebGL makes it possible to take advantage of hardwired graphics acceleration, allowing for dramatic speed and scale increases versus other mapping libraries. So here we have an interactive demo of 860,000 points. This is census data. essentially representing the population of New York in 2015. You can see it's fully interactive. And of course, you can see actually that we can update the visualization. Here's a visualization of earthquakes over time. So these are 218,000 earthquakes. You can see it's fully responsive in the same way the visualization above was. We can also play that data over time. So if we zoom in here, you can see how active these particular fault lines are. And of course, you can see where the ring of fire is. You can see where the individual fault lines are. And you can even see things like the fracking boom in Oklahoma, which ends up causing a series of earthquakes later in this visualization. Since deck.gl is a JavaScript library, it might not be the most accessible to data scientists. You can imagine geologists want to render the visualization we saw above, or actuaries might, and they might be more familiar with Python and less familiar with JavaScript. We figured a good way to create a cross-language spec for deck.gl and rendering visualizations declaratively would be through this JSON API. So essentially, any language that can write JSON can now write deck.gl visualizations. And if you go to this link here, that https:/deck.gl/playground, you can actually play around with this editor yourself, or of course, you can load up the iframe here in the notebook. Here we are in the editor. Let's change the pitch. The map repitches. Let's change the height. Let's also set that pitch back. Change the pitch, change the height. And you can see that it's fully responsive. As we modify these parameters around this hexagon layer, the hexagon layer actually changes shape. We can even change the base map. And there you go. So that's an example of using the deck.gl JSON API directly in this editor. You could imagine that as a Python user, you might not want to write a large block of JSON. So essentially, PyDeck is three libraries. It is a Python interface to this JSON API. It is at deck.gl/JSON, which converts a JSON config to a deck.gl visualization. And then it's at deck.gl/Jupyter widget, which connects a visualization to Jupyter Streamlit or Colab, often in a bidirectional way. Let's take a look at the JSON from our visualization before, the artificial signups visualization. So here's the output for that. And we can paste it into the JSON editor. And then see that PyDeck is more or less just writing JSON on your behalf. You can see that visualization is identical to the one we had before. PyDeck also aims to be interactive and easy to update. Here's a data set of blue whale migratory paths rendered over time. Each individual color represents one unique whale. You can imagine if you were a climatologist or an ecologist, you might be interested in knowing this data or having access to it, as well as playing it over time. And we can see PyDeck does not struggle with rendering these large volumes of updates. Things look relatively fluid. And of course, you can see the patterns in data, like the whales migrating towards California in the summer. And then by the time that winter rolls around, they'll head south. Let's just really quickly go through one PyDeck example line by line. So we'll use that data set from the JSON viewer before. This is a data set in the UK for 2014 motor vehicle accidents. The data set has within it the longitude and latitude of each accident. And let's just plot it. So here's one example. These are all the accident locations. We load the data in to, in this case, a Pandas data frame. We specify the kind of layer we want. You can look at these in the PyDeck docs to sort of have an idea of what the menu available to you is. We load in that data frame. We specify our data as the second parameter here in this layer. We specify get position, which is our X and Y value for our data set. Next, we also specify some parameters that are unique to a scatter plot layer, occasionally parameters shared by multiple layers. This auto highlight this radius min pixels here essentially says the visualization, no matter how far you zoom out from the map, will have to be at least 1 pixel. In other words, each point gets a minimum of 1 pixel. In this case, we have a fill color specified in RGBA format. So you have the layer, you have to have the viewport, essentially a camera angle relative to the viewport. It's the first angle the user sees. If you want to quickly find an appropriate angle for your data, there are a number of tools online to do this. I wrote one, so I'm going to use that really fast. If we go to, let's say, United Kingdom, we can copy and paste that viewport in, and we'll render everything. The last thing we need to do is, of course, bring our view state and our layer together. So there's our layer. Could also be a list of layers. Right now, we're just rendering one. In this case, we're going to take our view state. That's that angle of the camera relative to the map. We're also going to specify a Google-based map using satellite imagery. And here's our visualization. So we can see 1 point for every accident within the UK. Let's zoom a little bit closer here. Suppose we wanted a richer three-dimensional visualization, we can also aggregate the data to Hexagon. You can see that we have a tooltip now. We have this auto highlight going. And you can see the number of accidents at any particular location under a hexagon. Let's go through this visualization line by line as well. So here, instead of scatter plot layer, we're specifying we'd like a hexagon layer. We specify the same data set as before. This time we can see that PyDeck can also read directly from the URL. You don't necessarily have to load to Pandas first. We specify a couple parameters that are unique to the hexagon layer. I'd really recommend checking out the deck.gl docs to get an idea of what these parameters might do. Next, we specify the view state, much in the same manner we did before. Finally, we combine that view state with that layer to be able to render a map. And we'll also specify that we'd like a Mapbox base map in this case, as well as a tooltip. And you can see that we can actually render the tooltip using HTML. So we have a bolded number of observations there. And of course, then we render it. In this case, we're going to plot Geojson with GeoPandas. We'll load Geojson for all the hurricane locations for the last 150 years into PyDeck. You'll notice here we don't actually specify a position column. We just call the data frame directly. We specify that we'd like a Geojson layer. We specify that the layer can be selected, that the data shouldn't have an outline, that polygons, if they exist, should be filled, and a couple other parameters you can read a bit more about in the deck.gl docs once again. There's an example of what our data set will look like. The name of the hurricane, the geometry shape, the year of the hurricane, the maximum sustained wind in that hurricane. So here we have the paths for all the hurricanes for the last 150 years. We've also specified that the line color be rendered as an RGBA value, but the R and B values here are provided by the maximum sustained wind value. So PyDeck will look at that variable for maximum sustained wind and actually substitute that in. In this case, if the maximum sustained wind were actually 80 miles an hour, as it is here, the line color for that particular hurricane would be 80, 0, 80, 200, which is one of these darker segments of purple. The data set above is a little bit chaotic when visualized all at once, so it might be helpful to visualize the data over time. So here we see the data set for hurricanes rendered over time. Let's look a little bit about how this works. We take our layer from before, we specify our tooltip, we specify our map style, we put this all into the deck object like we've already done. We specify an IPyWidgets HTML object. That way we can display a year as the data updates. And then essentially this is our main method. We go and we play the data over time for the first year of the data set, the last one. We substitute out our data. We call deck.update in order to tell PyDeck that our JSON config has changed. We substitute in the new value for the year And then we pause a little before loading in the next year of data. I'd like to quickly show you how you can use IPy widgets plus Pydeck and a couple external tools to build some really powerful applications. We're going to talk about isochrones. Essentially, an isochrone is a geometry that answers the question, how far can I get from X point in Y minutes? So in this example below, here we are in the city center of Palo Alto. Within the green ring is everything that's reachable by car within 5 minutes. Within the blue ring is everything that's reachable by car within 10 minutes. You could imagine in the case of tourism, real estate, retail site planning, transportation planning, and much else, you might have questions that benefit from an isochrone. How many shoppers are within 20 minutes of my grocery store? How many points of interest are within walking distance of my hotel? Pydeck is capable, when combined with external tooling, in this case we're going to be using a route engine called Grasshopper, of interactively rendering these isochrones. It's worth calling out you'll need a local version of Grasshopper running on your machine for this demo. See the Grasshopper docs for setup. I'm using the Dockerized version of Grasshopper. You'll also need to install R-Tree in your Python environment, which may have some additional dependencies depending on what platform you're using. Also, last thing worth calling out, this demo will only work for Berlin, but you can configure Grasshopper to use other OpenStreetMap data. You can see GeoFabric, the link there, to get an idea of what your options are. I've written a Grasshopper client. This will reach out to Grasshopper and fetch an isochrone based on the latitude and longitude. I'll very quickly render one example isochrone. Here we are in Berlin, and this is how far you can get within 20 minutes from the city center of Berlin. So I'm going to combine one of these data sets from the Pydeck docs, this location of all the beer gardens in Germany according to OpenStreetMap. I want to answer the question, how many pubs are within 20 minutes of any particular click? So here, if we zoom into the city center of Berlin, we can see we have some beer garden locations. So here's Rosengarten, for example, located at that latitude and longitude. If we click, there are 38 points within 20 minutes of the clicked points. Essentially, these are how many beer gardens are within 20 minutes of the click. Here's another 9 points. Cool, 18 points. And you can see that Pydeck might be useful for certain kinds of geospatial applications that you might want to write, and you don't have to write a line of JavaScript to do it. This is also going to be one more example of a two-way application that I think is kind of interesting, as well as some other features of Pydeck that I don't really have too much time to go into, but want to show you at a high level. Here we're looking at a data set of concert performances by a set of artists. The data is from setlist.fm in case you're curious to extract it yourself. We have a unique ID for that performance. We have the artist in question, in this case, the band The National. We have the date the event happened, and then we have the name of the venue where it happened, the latitude and longitude, the city it was associated with, the tour name as well. We also have the previous location the National was coming from. Here, in this case, we're actually going to plot the data on a three-dimensional globe. And I'd like to draw on that globe essentially a line linking all the tour locations that a particular artist went to. So I'm going to actually specify a globe view. You can look at this in the Pydeck docs. Unfortunately, for these 3D globes, you can't really get the 2D tile data on it just yet. So we're going to bring our own custom Geojson layer as a base map. I'll do a little bit of data cleaning. I'm going to be adding a color to the tour. We'll take a look at how this random is used in a moment. Essentially, it's to keep lines from colliding with each other in the visualization. And then I'm actually going to specify this time 3 layers. We're going to specify our GeoJSON base map. We're going to specify an arc layer, essentially a line that will join where the artist was to where they're going next. This get tilt times random essentially takes that random value, multiplies it times this 15, and then provides a tilt value for the lines we'll see in a moment. Like I said before, this keeps them from colliding with each other. A scatter plot layer to highlight the city location. Essentially, each circle will represent a city or a venue. Our specialized globe view is passed here. We have to set map provider equals none to tell Pydeck we don't want a base map. It assumes you usually do. And here is the visualization. So here for the recording artist, John Legend, we can see all of his tour locations for the entirety of his career. You can see also the tour names. This is only as good as the data from setlist.fm is, but I think it's probably pretty good. Here we can see a European tour. We can change the artist. So let's take a look at Daft Punk. Bob Dylan. National. Beyonce. Looking at this tour map, I hope you get a sense for how PyDeck can be used for richer applications. I'd like to talk about some other features that we didn't get as much time to cover as I would like. In the catalog of available layers, you can see at pydeck.gl, that's our website. Other spatial projections, so we talked a little bit about the globe view. We haven't talked about the orthographic projections or anything of that sort. Custom layers, our Google Earth integration is actually a PyDeck custom layer, and you can check that out. And of course, like I said before, I really recommend taking a look at the docs in case you're curious to learn more. I also want to talk about what will change. PyDeck is a relatively young library and has a lot of space for improvement. A lot of you have requested legends. We will be adding legends to PyDeck, some better defaults so that you don't have to configure as much about a visualization. There are certain cases in PyDeck where you don't get as much information back from the error message as I would like. More two-way interactive environments, so we'll have support for Streamlit and Colab in the same way you saw our Jupyter widgets integration work. We'll have improved support for time-based updates, and of course, much more. Follow our release tracker tasks on GitHub, join our Slack channel, and of course, feel free to tag me or message me directly with issues. Just a quick thanks to the team, and a particular thank you to the Urban Computing Foundation for supporting the project, and especially a thank you to JupyterCon for having me and you for showing up. Feel free to tag me in any awesome visualizations you might have, and feel free to message me with questions. Thank you, guys.